Hi everyone, I'm Davide Paglieri, AI researcher at Bending Spoons. And today I will be presenting SlowMo.ai, my work on video frame interpolation. The goal of video frame interpolation is to synthesize new frames in between adjacent frames of a video. This is done so that we can upsample the frame rate and have a smoother playback, or keep the same frame rate and have a slow motion effect. Key to video frame interpolation are optical flow and backward and warping. Optical flow is the pixel displacement between adjacent frames. So for example, given a pixel at time t with coordinate x and y, this pixel can move, and at time t plus the t will have coordinate x plus dx and y plus dy. Dx and dy are the displacement vector, and this is called optical flow. So we can represent optical flow as a dense map in the HSV color spectrum. So here the color tells us the direction of the displacement vectors, and the intensity tells us the magnitude. So we can see here that the leg of the flamingo is moving from left to right. The other key is warping. So let's say that we have a video of this car moving. We can take 2 frames of this video and estimate the optical flow between them. Now let's say that we want to get a frame in between frame 1 and frame 2. Having the optical flow from frame 1 to frame 2, we can take frame 1, and for each pixel we'll use the displacement vector and see where it will land towards frame 2. So we can take each pixel and do this mapping. We will see that multiple pixels sometimes will be mapped into the same positions, and we can solve these collisions by applying a technique called softmax plotting. And there will also be cases in which no pixels have been mapped to that position. And in this case, these are holes, and we can solve them by estimating the bidirectional optical flow from frame 1 to frame 2 and from frame 2 to frame 1, and forward warp both frames towards the desired position. We can then use a fusion network to fuse together these frames and get the final result. Another option for warping is called backward warping, and as the name suggests, does the opposite of forward warping. So taking optical flow from frame 1 to frame 2, we can get back an image frame 1 starting from frame 2. So starting from a blank matrix, for each pixel we will look up its position in frame 2 and interpolate its colors. There will be cases in which pixels will stay put. However, in the next frame they will be occluded by the moving image. So for example, here the front of the car, in one frame it will have the grass, but in the second frame we have the car itself. So we can see that when doing this warping we have a redundancy. And this redundancy can be solved in the same way that we solve it with forward warping with holes, and it is by estimating the optical flow bidirectionally, doing the warping bidirectionally, and fusing them together using a synthesis network. And this is the result, for example. We found out experimentally that for recursive interpolation, backward warping has the upper hand. What I explained was the simplest way to do video frame interpolation, and now I will explain some challenges. So for example, the biggest challenge in frame interpolation is handling large motion. So here we can see that the leg is moving a lot between 2 adjacent frames, and optical flow will have problems understanding the displacement, and it will fail in case of like this. Another problem is retaining sharpness when warping frames. If we don't do it properly, we will lose these sharp details. And finally, occlusion between objects can also cause problems in the optical flow estimation. I will now show the method that we use for this, and this is the main network, and I'll also explain how we try to solve some of these problems. This network is inspired by frame interpolation for large motion, and the way that it works is that we take as input, given a triplet of frame, we take the first frame and the third frame, and the ground truth will be the second frame. We start the processing by downsampling bilinearly these 2 input frames. We then apply a feature extraction network to get features at different scales. Then using these features, we estimate the optical flow, and we do this starting from the lowest resolution to the highest resolution. We do this bidirectionally, and we backward work both of these extracted pyramids toward the desired position. And finally, we use a synthesis network that starts from the lowest resolution to the highest resolution, and which gets back the image. And in the end, with a super resolution module, we get back the original, the final image at the original resolution. The reason why we do this processing in multiple scales is to handle large motion better. This is because if we halve the resolution of the image, then the optical flow, the magnitude of the displacement, will also halve. Furthermore, the processing, the inference time of the main network will also be shorter if we reduce the resolution. The loss that we use is the style loss from film, and it is made up by the L1 loss, the perceptual loss with VGG network, and the ground matrix loss with VGG network. And this helps us retaining sharp details. Here we show some qualitative comparisons of our method. We don't show benchmark comparisons as our method is more geared toward real-world usage, and this is due to the fact that we apply a lightweight super-resolution network. And the reason for this is that the upper bound PSNR score will be limited by our super-resolution network. We choose to use a light one for having a smaller processing time. Here is the comparison with DaVinci. DaVinci is the state-of-the-art video frame interpolation software available on commercial softwares. And on the right is our method. You can see that our method handles large motion better than DaVinci, and you see that the hand, despite not being perfect, moves smoother, and the same goes for the bricks falling. These are some comparisons with other methods. We have many-to-many splatting and film here. You can see DaVinci, when warping, warps the fingers together. Many-to-many splatting has some ghosting artifacts. Film does a better job, however, the hand has a kind of a natural shape, the fingers are not the proper length and it's a bit blurred. While our method retains sharpness and it also doesn't warp the fingers unnaturally. Here you can see a video of a dolphin swimming, and this is the result of our method in 8 times interpolation. You can see that it's quite smooth and it handles the motion of the dolphin very well. Our method is available on app.SlowMo.ai. The front end is curated by Alessandro Berlati and the back end is done by Riccardo Albertazzi. The distributed processing on the back end works in the following way. When the user uploads a video to the cloud storage, this video gets split into frames, individual frames, and according to the availability of GPU workers, we send these frames into batches to the GPU workers, which apply the model for video frame interpolation. When they are done, they will encode the frames back into a video and send it to the cloud storage. And finally, we concatenate these videos and send it back to the user. Despite our effort in handling large motion, our method still fails with very large motion. You can see here how the hands, how the arms and the legs are kind of disappearing and are also dragging the background with them. And this is due to both failures in optical flow due to the large motion, but also due to the inherent blurriness of the original video. You can see here, for example, some original frames of the video, and these are have some blurriness to them, and also the arms here. And these blurry frames will create problems with optical flow, which will both not be estimated correctly, but also will have a larger area, which causes the dragging of the background. So in the future, what we want to do is we want to train a video frame interpolation, video super resolution, and video deblurring all jointly into a single network. And this can be done efficiently using the same optical flow for all three operations. Thank you for watching, and if you have any questions, I'm looking forward to answer them at the poster session.